designing hands upper limb prosthetics for over 90 years. And this is the field I'm going to be discussing today. I started life out as a designer at RSL Steeper. If you think about your hand, it is an amazing thing. You can hang your own body weight from it, but you can also use the same tool to paint a picture. It's got a waterproof cover. It feels the environment around it. It can feel hot and cold. It can also regenerate itself. It comes in a massive range of sizes and colours. You've got two styles. You've got left and right. So as a design brief, it is a pretty challenging one. There's a lot of university research and military research going on at the moment, absolutely replicating the arm as it is. All the degrees of freedom, all these features that we have. But this really isn't where I'm coming from. What we wanted to do was take what the essence of a hand was and then effectively boil it down to something we could use today's technologies for helping a lot of people. Effectively, someone could take the existing hand off, plug ours on, and they could be going in 30 seconds. Okay, so the idea of upper limb prosthetics isn't a new one. A Roman general actually had a metallic hand which held a shield. And through the 18th and 19th century, surgical techniques improved and people started using simple mechanical hands. So you would have a cable across your shoulders, you'd pull them in, and you would be able to open and close a hand. Through, sadly, demand drives innovation, and World War I, there was a lot of people who needed this type of device. And then again, there was a lot of development in the aircraft industry after World War II, and a lot of that technology was adopted. In the 1950s, a team of scientists at the University of Munich developed they actually found the myoelectric signals that are sent from the brain to activate muscles. And from there, obviously that has a massive advantage for driving a prosthetic. A user can think close hand, and the hand will close. And they first commercialized that in 1960, so people were able to get a myoelectric arm in 1960. Okay, perfect. So the myoelectric sorry, next slide. Okay, so this, back again, cool. So this just shows a schematic of the standard myoelectric forearm, which has been around since about the 1980s. You've got a soft liner which goes onto the remaining stump, which has an electrode on the inside and on the outside. The battery system and wrist interface is mounted in a hard outer shell, and then the hand is clipped onto that. With training, a user is able to give an open signal, a closed signal, and also what's called a co-contraction signal, which is a fist, and that fires both electrodes. So the hand that you can see on here is effectively a generic design for a myoelectric hand. It's a simple three-jaw chuck design with a fixed linkage between fingers 1 and 2 and the thumb, and it just goes through a standard pinch system. You can get a fantastic grip with something like that. It's very powerful, but it's not compliant. So if you're holding a wine glass or a disposable plastic cup, something like that, it's very difficult to get control. Also, something like an umbrella is quite difficult because you've got a big gap. People have to add foam to everyday objects to be able to get a good, strong grip of things. So the design idea that we came up with was to take that system from the wrist and then see whether we could push the boundaries, see how much we could do, knowing what the clinical technology was out there. So we weren't going to do anything with that system. We were just putting the best hand on that wrist. We wanted to make it as natural as possible, so it looked like a hand. We also wanted to make it as basically compliant, so you could grab a piece of fruit or, as I say, a wine glass, and you can get a nice stable grip on it. The natural form, I think Andreas is going to discuss later on in his talk, but it has more advantages than just looking good. The actual person feels better because it looks like a hand. We also sort of stole this idea from Apple, but we also wanted people to have joy in using this product. We didn't, I don't think there's been a great deal of excitement about designing prosthetics, but we wanted people to go, wow, I want one of those. Next slide, please. So, as a designer, which is where I started, it's a strange thing to start to design. Obviously, you've got your benchmark product on the end of each of your arms, and you know it intimately, so you know exactly what it's got to do. But you're also designing a product that you've never used. You've never used a prosthetic, and hopefully I won't have to. So it's a really unusual thing to have to design. We had to build a lot of relationships with amputees to understand what would be a useful feature and what would be a hindrance. And we have a team of guys all over the world who feed back ideas, and they are going into development as we speak. Also, where you start with a project, a normal project, would be you'd get a stylist, and this thing would be sketched, and the engineers would end up having an envelope that they had to work within. But as you start with a hand, you haven't really got that. We didn't want to just get an average person and scan their hand and then build our structure around it. We need something, it's called parametric, so we are able to change the design as we go along. So we took the 50 percentile American male, and we took all the measurements and built a virtual skeleton just with vector lines. And from there, we were able to build up a structure. But that also gives us an advantage that if we need to change the structure because of a design constraint of a motor, we're able to do that rather than having to go back and then find someone who's got a slightly bigger hand or a slightly smaller hand and scan them. So that was that's the concept. We also had to drastically simplify the motions of the hand. Obviously, you can do all sorts with your hand, but fundamentally, there's a limited amount of grips that would get you sort of 50%, 60% of functionality. So we took the fingers on this. Obviously, we can move distal and proximal independently, or some people can. But these fingers move in a simple trajectory. So they can get a pinch grip, but they can also roll into a fist. So when we had that skeleton, we were therefore able to, if I do. So we can also do this. It's called finger abduction. And it's quite useful for holding cutlery, holding pens. The way we got around this is we actually rotated all the trajectories in. So they all, as you come in, it goes into it rolls together. So the user can actually get a partial grip and get a pen or a piece of cutlery in there. The thumb design, again, very interesting. I spent a lot of time looking at my own thumb and trying to work out how I was going to do this. Effectively, we went for a similar approach to the finger, a single trajectory, but with two start points. So this will give you an opposed grip. But then the user is able to knock it over to one side, and then there's a secondary grip in there as well. So you've got that. Okay, so we've got the concept, we've got the thumb and we've got the finger sorted out. Can I have the next slide, please? We made a fatal error in the development. We took our own hand and we did some strange research to try and work out what it takes to break a human hand. And you're thinking, well, I'm designing a hand, that's what it's going to benchmark against. This is a mistake for a prosthetic. The issue is that the hand is compliant. Your hand is compliant. So if you, say, for example, falling over, as you go to fall towards the surface, your hand automatically, it opens and it forms the shape of the thing you're going to hit. This spreads the load over the full palm, reducing the force. So with something like this, as you fall, it's hard. You know, the first thing that hits the surface is going to break, which is no good as a prosthetic. If it's your hand and it's broken, it's no good. The other issue that we had in our design is we didn't the feedback mechanism that our hands give us. So if I smack my hand against this table, it's going to hurt, but so I won't do it again. So if I do other exercises that cause me pain, I avoid those as well. So it becomes a learned exercise. Whereas with this type of product, there's no feedback mechanism. So if you do something and it breaks, that's the only feedback mechanism you've got. So again, that was another an error we made. The last error we made is we didn't think like the end user. We thought like engineers. We designed a product which it had all the really expensive high precision motors, PCBs, safely locked away in the palm as close to the body as possible. And we made the fingers fairly lightweight, out of plastic. And the idea was that if you broke them, you'd basically have loads of fingers and you could just clip them in and that would become a learning process. We made fuses which broke at a certain level. So you could, basically, if you broke a finger, you put a fuse in with a pair of pliers and your finger's back up again, which is fine if you're technically minded. If you're not, and you've only got one arm, and you're a plane ride away from the clinic where you got the hand from, it's unacceptable. It isn't going to work. Okay, next slide. So we effectively took, in English, it's a belt and braces approach. So we threw everything at it. We changed the chassis structure to CNC machined aluminium. So you've got these two knuckles here which are fully integrated into the chassis. So it's absolutely rock solid. The proximals are made out of stainless steel. You've got stainless steel crosslinks. You've also got seal cartridge bearings on all of the fingers, which gives you an incredibly strong base for the fingers. We went from 16 kilos, which is what we think would break a human hand, to 40 kilos to break one finger. So with two fingers, you can pick up someone's body weight. So it's beyond the normal usage. We've also got full metallic structure on the thumb. So again, it's engineered beyond what the human hand can take. The general rule was, if you can break this, it's not the right product for you now. You know, it's so strong that you're doing something wrong with it. So, can I have the next slide, please? Okay. We had another challenge, which was people have been used to just having an open and closed signal, which literally open and closed, the Myoelectric. And this hand can do a massive range of grip patterns. The way the system works is you've effectively got two thumb positions, which are manually operated. You can knock it to opposed, and you can give it a closed signal. You open again, and you get a secondary grip. You then knock the thumb over, you get a closed signal, and repeat the exercise again. So from there, you've got 4 grips. You can then press, there's a button on the back of the hand, you can press that, and you can get another set of 4 grips. So if someone wanted to use 8 grips, they can do that. We also have a push and hold, which puts it into like a glove mode. So we actually thought of this for, we have a silicone cover that goes over that looks like skin. We made it so you could get that on easily, but we actually, people found it easy to put jackets on so they can get it through clothes. So that's actually used. So we also, so the user can pick any one of those grips and build up a system in the clinic. If they want a particular grip at a particular place, they can get that sorted out. There's also threshold and proportional, which means that if you've not got particularly good control of your muscle, you can have threshold system where it will just use at maximum speed once a signal's reached a certain level, or proportional where someone could give a weak signal and it would go slowly, or a strong signal, it would go faster. So we basically, the way we did it was with an encoder system. So every time a motor rotates, it counts. And with that, we can build up a matrix of, for every grip, there is an encoder value for each fingertip position. So if you imagine tripod, which is the 3 finger, those independent motors have got to converge exactly at the right time, again and again and again. So it's quite a challenging control system that runs the hand. Next slide, please. We also put a few features in, which was the hand rolls up into a fist. So the idea was if someone was falling, it would try and get the fingers out of danger. We also found that amputees found this incredibly addictive because they can talk and they can manipulate the other hand. So we actually increased the life of the springs because of people just playing with their hands rather than using it as a hand. We also put two-way adjustment on the thumb so people can actually tune the perfect position of where they want the pinch. And you can see the chain link system, that's part of as it folds up. We put soft palps on the end of the fingertips so people can get a more stable grip of objects. Okay, so next slide, please. So you've got, basically the product's been out since September, and it does what it says we set out to do. We can have someone who's run a myoelectric hand for 10 years, and we can take that hand off and plug our hand on, and within 30 seconds, they can roll their hand into a fist or finger point for the first time ever. So that changes someone's life. They've actually got a hand back rather than just something that grips. I've also been sent videos of people drawing, people riding a bike. I've even been sent a video of a guy firing a shotgun. You know, we don't recommend using firearms, but it does give you the idea of the confidence that people put in this product. The strange thing is we've had quite a lot of demand from able-bodied people saying, I just want one. Can you? You know, it's a crazy idea, but we've created something that people who don't need one want one. So I think that's worked as a concept for changing people's perception of prosthetics. So, next slide, please. So the future, and we've gone a small way along this road, to be honest. This is sort of 10%, 15% of the functionality of a human hand. We've got some new projects. We're going to make some smaller ones because ladies have very small hands, I've discovered. And they don't want a three-finger hand. So we're going to have to go back to the drawing board and work out what we're going to do. We're also doing extra sensitive electrodes. We're looking at a partial hand system. So it's quite common for people just to lose their fingers rather than the whole hand. So that's another thing we're doing. We're working with a team who, a really clever idea, to be honest. They use RF chips, which basically react to being in the proximity of a transceiver, which basically means their local environment, they can stick these tiny little stickers all over. So the keyboard, it can come in the proximity of the keyboard and it'll go into finger point mode without even thinking. They can also have, in the lapel of the jacket, they could have one that put it into glove mode and then the other one at the bottom that opened the hand again. So an amputee could chuck on the jacket, not even think about the hand, and it did what it needed to do to get down the sleeve. So the more you think about that, the more you think it would be fantastic. But fundamentally, what would radically change people's lives is a new standard myoelectric socket system, which effectively had a two-way communication, so it would give feedback. We would be able to put sensors in the hand and feed that back to the user. There's also a lot of work gone on to pattern recognition, which is using the two electrode systems that we've got now and building up a pattern. It's a really strange thing, but it's where the body actually works against us. People can generally generate about 4 discrete signals, and then as they practice these 4 discrete signals, they diminish, they disappear. So in 6 weeks, they're gone, and they're gone forever. It's a little bit like a golfer. If the first time he goes and does 18 holes, we'd be able to pick up a signal every single time. But if he became pro, practice and practice and practice, we put the same measurement system on him, we wouldn't pick a signal at all. So it's these sort of rapid nerve signals, they disappear to a level where we can't pick them up. There's a lot of work on selective muscle targeting, so people will actually have surgery and have nerves replanted in, so the nerves that went to the hand to chest muscles. Again, it takes about a year of surgery to get that sorted and start to get in the benefits. But fundamentally, we've made sort of a small step along this road. We've changed people's lives, and it's not so much just the additional functionality, it's how people feel, that people are making them more confident, and it's breaking down the barriers that prosthetics sometimes can create, which must be a good thing. Thank you very much.